For most of human history, the idea of a sky ruled by more than one sun belonged entirely to myth and imagination. Ancient legends spoke of twin suns as omens of chaos or divine judgment. Modern science fiction turned them into exotic backdrops where shadows fall in opposite directions and days never truly end. Yet the universe, vast and unapologetically strange, has revealed something astonishing. Worlds with two suns are not fantasy. They are real, and they are far more common than anyone once believed. Our own solar system is built around a single star, the Sun, and for a long time astronomers assumed this was the normal way planetary systems formed. One star, surrounded by planets, dust, and debris. Simple, orderly, familiar. But as telescopes grew more powerful and surveys expanded beyond our galactic neighborhood, a startling pattern emerged. Many stars do not live alone. In fact, a large fraction of stars in the Milky Way are part of binary or even multiple star systems, where two or more stars are locked together by gravity, endlessly orbiting a shared center of mass. This realization changed everything. If stars commonly come in pairs, a question naturally follows. Can planets exist in such systems? Can a world survive under the gravitational pull of two suns? And if it can, what would such a sky look like? What would such a year feel like? And could life ever emerge in such a place? Binary star systems are not rare cosmic anomalies. Roughly half of all sun-like stars are believed to be in binary or multiple systems. Among massive stars, that number climbs even higher. The galaxy is filled with stellar pairs dancing around one another, sometimes close and violent, sometimes distant and serene. For decades, astronomers suspected that the chaotic gravitational forces in these systems might prevent planets from forming at all. The tug-of-war between two stars seemed too disruptive, too unstable for the delicate process of planet formation. That assumption turned out to be wrong. The first hint came quietly. In 1993, astronomers discovered a planet orbiting a pulsar in a binary system, an extreme and hostile environment. It was an oddity, not a revelation. But in the following decades, as exoplanet detection methods improved, evidence began to pile up. Planets were being found in binary systems again and again. Some orbited one star, while a distant companion star loomed in the background. Others followed a far stranger path, circling both stars together, like a cosmic tightrope walker balancing between two suns. These are known as circumbinary planets. Circumbinary planets do not orbit a single star. Instead, they orbit the combined gravitational center of two stars. From the surface of such a world, the sky can be breathtaking and unsettling. Two suns rise and set, sometimes together, sometimes apart. Shadows stretch, overlap, and vanish. Seasons are unpredictable. The concept of a year becomes complex, shaped by the intricate dance of two stellar bodies. The first confirmed circumbinary planet around a sun-like binary system was announced in 2011. It was named Kepler 16b, discovered by NASA's Kepler Space Telescope. This moment marked a turning point in astronomy. For the first time, a real planet was confirmed that mirrored the iconic imagery of science fiction worlds like Tatooine from Star Wars. A planet with two suns was no longer a thought experiment. It was a measurable, observable reality. Kepler 16b itself is not Earth-like. It is a gas giant, similar in mass to Saturn, and likely inhospitable to life as we know it. But its existence proved something crucial. Planet formation can occur even in the complex gravitational environment of a binary system. Nature, it seems, is far more adaptable than human intuition. To understand how such planets exist, we must first understand the structure of binary star systems themselves. Not all binaries are alike. Some stars orbit extremely close to one another, separated by distances smaller than the orbit of Mercury around our Sun. Others are so far apart that they barely influence each other's planetary systems. The distance between the stars, their masses, and their orbital eccentricity all determine whether planets can form and where they can survive. In wide binary systems, planets often orbit just one of the stars. These are known as S-type orbits. The second star appears in the sky as a bright companion, sometimes outshining all other stars, but exerting relatively little gravitational influence on the planet's immediate environment. In such systems, planetary motion can remain stable for billions of years. Circumbinary planets, on the other hand, exist in P-type orbits, where the planet circles both stars. These systems are far more delicate. If a planet forms too close to the stars, gravitational chaos can fling it into space or send it crashing into one of the suns. If it forms too far away, it may never coalesce at all. There exists a narrow zone of stability, a cosmic sweet spot where a planet can endure. Finding these planets is extraordinarily difficult. Traditional detection methods struggle in binary systems because the light from two stars interferes with precise measurements. The Kepler Space Telescope overcame this challenge by observing transits, tiny dips in brightness that occur when a planet passes in front of its stars. In circumbinary systems, these transits are irregular and complex, reflecting the constant motion of the stars themselves. Each detection requires patience, precision, and years of observation. As discoveries accumulated, astronomers began to notice patterns. Circumbinary planets tend to orbit just outside the critical radius of instability, as if nature places them exactly where survival is possible and no closer. This suggests that planet formation in binary systems is not random chaos, but a structured process shaped by gravitational boundaries. But what does it mean for habitability? The concept of a habitable zone, the region around a star where liquid water can exist on a planet's surface, becomes vastly more complicated when two suns are involved. In a circumbinary system, the combined energy output of both stars determines the habitable zone. But because the stars move relative to one another, the zone itself can shift, expand, and contract over time. A planet in such a system may experience dramatic climate variations. Long periods of relative stability could be punctuated by extreme temperature swings. Seasons might not follow simple annual cycles. Ice ages and heat waves could be triggered not by planetary tilt, but by the orbital dance of the suns themselves. Yet complexity does not equal impossibility. Computer simulations suggest that under the right conditions, circumbinary planets could maintain stable climates over geological timescales. Oceans could persist. Atmospheres could endure. And if life is as resilient as it appears on Earth, it may adapt to rhythms far stranger than our own. Binary systems force us to rethink what normal means in the cosmos. They challenge the idea that life requires simplicity. Instead, they hint that life may thrive amid complexity, adapting to skies with two dawns, two sunsets, and nights that are never truly dark. As we continue to search the galaxy, binary star systems may prove to be not obstacles to life, but vast, untapped arenas where nature experiments with new possibilities. To understand how a planet can exist beneath two suns, we must return to the very beginning of a star system's life, long before planets have names or surfaces, when everything is still dust, gas, motion, and gravity. Planet formation is already a delicate process around a single star. In a binary system, it becomes a cosmic gamble, shaped by forces that pull, twist, and tear at the material trying to come together. Every planetary system begins inside a molecular cloud, a cold, dark region of space filled with hydrogen, helium, and trace elements forged in earlier generations of stars. When part of this cloud collapses under gravity, stars are born. In many cases, that collapse does not produce one star, but two. These twin stars form together, bound by gravity from the very start, spinning around a common center as if locked in an eternal embrace. Around these newborn stars, disks of gas and dust emerge. These protoplanetary disks are the cradles of planets. In single-star systems, the disk forms a relatively flat, orderly structure where particles gently collide, stick together, and slowly grow from microscopic grains into planetesimals, then into full-fledged planets. In binary systems, the disk is anything but peaceful. The gravitational pull of two stars can warp the disk, creating spiral arms, gaps, and shock waves. Material may be flung outward or dragged inward. Collisions between particles become more violent. At first glance, this environment seems hostile to planet formation. For many years, astronomers believed that binary stars would simply shred their disks before planets ever had a chance to form. But nature is persistent. Observations from powerful observatories, such as ALMA, the Atacama Large Millimeter Array, have revealed that protoplanetary disks do survive in binary systems. Not only that, they often show clear signs of planet formation. Rings, gaps, and asymmetries in these disks suggest that material is clumping together, resisting chaos, finding ways to organize itself despite the competing gravitational forces. The key lies in location. In wide binary systems, where the stars are far apart, each star can maintain its own disk. These circumstellar disks behave much like those around single stars, allowing planets to form in relatively stable environments. The distant companion star acts more like a distant sun in the sky than a disruptive force. Planets forming here may never directly orbit both stars, but they still live in a binary system, experiencing a sky that changes subtly over long timescales. Circumbinary systems are far more complex. Here, a single disk surrounds both stars, rotating around their shared center of mass. Near the stars, gravitational interactions are intense. The stars carve out a central cavity in the disk, a region of instability where material cannot remain for long. This cavity is not empty by accident. It is a boundary enforced by gravity, marking the inner edge where planets cannot survive. Beyond this boundary, however, the disk can become surprisingly calm. In these outer regions, dust grains collide and stick, forming larger aggregates. Over thousands and millions of years, these clumps grow. Gravity takes over, pulling material inward, shaping protoplanets. Simulations show that once these bodies reach a certain size, they become resilient, able to maintain stable orbits even as the two stars continue their gravitational dance. One of the most intriguing discoveries is that circumbinary planets often form farther out in the disk and then migrate inward. Interactions with the disk cause them to slowly spiral closer to the stars until they reach the inner edge of stability. There, they stop, as if parked by an invisible gravitational wall. This explains why so many circumbinary planets are found just outside the critical instability zone. It is not coincidence. It is the natural outcome of formation and migration under dual gravity. Yet formation is only the first challenge. Survival is the next. Binary stars rarely orbit each other in perfect circles. Many follow elongated, eccentric paths. As the stars move closer and farther apart, their combined gravitational influence on a planet changes. This can pump energy into the planet's orbit, stretching it, tilting it, or even destabilizing it entirely. Only certain orbital configurations remain stable over billions of years. Some planets are lost. Models suggest that many young circumbinary systems may form multiple planets, only to lose some of them through gravitational interactions. Planets may collide, be ejected into interstellar space, or fall into one of the stars. The survivors are the ones we detect today, the end products of a long and violent evolutionary process. From the surface of such a planet, this history is invisible, but its consequences shape everything. The length of the year, the pattern of seasons, even the tilt of the planet's axis may be inherited from this chaotic beginning. Stability in a binary system is never absolute. It is a balance constantly maintained against disruption. Energy input from two suns further complicates the picture. Unlike a single-star system, where stellar radiation is relatively steady, circumbinary planets experience fluctuating energy levels. As the stars orbit each other, their distance to the planet changes, altering the amount of heat and light the planet receives. These variations can be small or dramatic, depending on the system's geometry. In some cases, these fluctuations could drive extreme climate cycles. In others, the effects may average out over time, producing long-term stability. The outcome depends on orbital resonance, stellar mass, and distance. Once again, complexity does not guarantee destruction. Under the right conditions, balance emerges. The realization that planets can form and persist under two suns forces astronomers to confront a deeper truth about the universe. Order does not require simplicity. Stability does not require isolation. Even in environments shaped by competing forces, structure can arise, persist, and evolve. Binary star systems are not cosmic mistakes. They are natural outcomes of star formation, and the planets within them are not rare exceptions. They are proof that planetary architecture is far more diverse than once imagined. To imagine a planet with two suns is to unlearn everything instinctive about time, light, and rhythm. On Earth, the rising and setting of a single star defines our days, our seasons, our biology, and our sense of order. One sun gives us a predictable sky. Two suns transform the heavens into something dynamic, theatrical, and often unsettling. On a circumbinary world, the sky is never still, and time itself feels different. From the surface of such a planet, the most immediate difference is visual. Two suns dominate the sky, each with its own color, brightness, and path. In some systems, the stars are similar in size and temperature, creating twin golden disks that rise together and set together, casting overlapping shadows across the landscape. In others, one star may be larger and brighter, while the second is dimmer, redder, or smaller, producing a primary sun and a companion that lingers like a glowing ember. These suns do not follow simple arcs across the sky. Their motion is governed not only by the planet's rotation, but by their orbit around each other. Sometimes they appear close together, nearly touching, their light blending into an intense brilliance. At other times, they drift far apart, stretching across the sky, creating long, complex shadows that move in unexpected directions. Days on a circumbinary planet can be long or short, regular or irregular. In some configurations, one sun may rise while the other is still setting, extending daylight far beyond what we experience on Earth. True darkness may be rare. Twilight could last for hours, bathe in the combined glow of two fading stars. Nights, when they come, may feel profound and unsettling, as if the universe itself has momentarily withdrawn its attention. The concept of a year becomes even stranger. On Earth, a year is defined by a single orbit around a single sun. On a circumbinary planet, the year is shaped by the combined motion of the planet and the binary stars. This creates multiple overlapping cycles. There's the planet's orbit around the pair, the stars orbit around each other, and the planet's own rotation. These cycles can interfere with one another, producing seasons that do not repeat in simple patterns. Seasons on such a world may be erratic. A warm period might last longer than expected, followed by a sudden plunge into cold when the stars align in a way that reduces the planet's received energy. Ice ages could be triggered not by slow geological shifts, but by orbital resonances. Climate history on these planets could be written in sharp transitions rather than gentle curves. Yet stability is not impossible. In systems where the stars are close together and the planet orbits at a sufficient distance, the combined light of the two suns can behave almost like a single source over long time scales. Temperature variations may smooth out. Oceans may buffer extremes. Atmospheres can redistribute heat, softening the impact of fluctuating stellar input. In these cases, life could find a foothold. Biology, however, would adapt to rhythms unlike anything on Earth. Circadian cycles, the internal clocks that govern sleep and activity, might be influenced by complex light patterns. Life forms could evolve sensitivity to both suns, using changes in brightness, color, or angle to regulate behavior. Photosynthetic organisms might develop pigments capable of absorbing a wider range of wavelengths, harvesting energy from two different stellar spectra. Plant-like life could grow in unusual forms. On Earth, plants orient themselves toward a single sun. On a circumbinary world, growth might be more symmetrical or dynamic, responding to shifting light sources. Forests could appear denser, layered, or shaped by ever-changing shadows. The landscape itself might reflect the motion of the sky. For intelligent observers, the psychological impact of a double sun cannot be ignored. Two suns would dominate culture, myth, and identity. Concepts of balance, duality, and cycles would be embedded deeply in philosophy and art. Timekeeping systems would be complex, tied not to one celestial body, but to an intricate celestial dance. Astronomers on such a world would develop a profound understanding of orbital mechanics early in their history. The sky itself would be a constant reminder that motion is relative and stability is earned, not assumed. Eclipses where one sun passes in front of the other would be spectacular and frequent, turning the sky into a living clock. Even shadows behave differently under two suns. Objects cast multiple shadows that shift and merge throughout the day. At times, shadows may disappear entirely when the suns align. At other moments, they stretch in opposing directions, creating visual confusion and depth. Navigation, architecture, and art would evolve under these conditions, shaped by light that refuses to be simple. Life under two suns would not necessarily be harsher, but it would be more variable. Adaptation would favor resilience, flexibility, and tolerance to change. Species unable to cope with shifting conditions would vanish. Those that thrive would embody the planet's chaotic elegance. From an astronomical perspective, these worlds are not curiosities. They are laboratories. They allow scientists to test the limits of habitability, to understand how climate systems respond to complex forcing, and to explore whether life requires predictability or merely persistence. The discovery of potentially habitable circumbinary planets has expanded the search for life beyond the comforting simplicity of single-star systems. It has forced scientists to ask deeper questions. Is Earth typical, or merely one solution among many? Does life seek calm, or can it flourish in cosmic motion? For centuries, planets with two suns existed only in imagination. Then astronomy caught up. When modern telescopes began to peer deeply into our galaxy, binary star systems transformed from abstract theory into observable laboratories. What scientists found within them reshaped our understanding of how planetary systems form, survive, and evolve. The breakthrough came with NASA's Kepler Space Telescope, a mission designed to answer one fundamental question: how common are planets in the Milky Way? Kepler stared at a single patch of sky for years, measuring the brightness of over 100,000 stars. When a planet passed in front of its star, Kepler detected a tiny dip in light. This method, called the transit method, was already challenging for single stars. For binary stars, it bordered on impossible. Yet the universe cooperated. In 2011, astronomers announced the discovery of Kepler 16b, the first unambiguous circumbinary planet orbiting two sun-like stars. This world instantly became iconic. It validated decades of theoretical work and provided the first real example of a planet moving around a pair of stars. Kepler 16b is a gas giant roughly the mass of Saturn. Its two stars, one slightly smaller than the Sun and the other significantly dimmer, orbit each other every 41 days. The planet itself takes about 229 days to complete one orbit around both stars. From the surface of Kepler 16b, the sky would be dominated by two suns of different brightness. Eclipses would be frequent. Seasons would be governed by the orbital dance of the stars. While Kepler 16b is far too cold and gaseous to host life, its discovery proved that circumbinary planets are not rare accidents. They are natural outcomes of star formation. Kepler did not stop there. Over the following years, the telescope identified a growing family of circumbinary worlds. Kepler 34b and Kepler 35b are both gas giants orbiting binary systems where the two stars are remarkably similar in mass and brightness. These systems produce skies with nearly equal twin suns, rising and setting in intricate patterns. The planets themselves follow stable orbits despite the strong gravitational forces at play, confirming that long-term stability is possible even in near-symmetric binary systems. Kepler 47 stands out as one of the most fascinating discoveries. It is a circumbinary system with multiple planets. At least 3 planets orbit the same pair of stars, making it the first known multi-planet circumbinary system. One of these planets, Kepler 47c, lies within the system's habitable zone, the region where temperatures could allow liquid water to exist under the right conditions. Kepler 47c is not confirmed to be Earth-like. It is likely larger than Earth, possibly a gas or ice giant. But its location is profoundly important. It shows that the habitable zone around binary stars is not empty. Worlds can exist there, and if large planets can, then smaller rocky planets may as well. Another intriguing system is Kepler 453b, often called a temperate circumbinary planet. It orbits its 2 stars in about 240 days and receives a level of stellar radiation similar to what Earth receives from the Sun. Its orbit is slightly tilted relative to the binary plane, causing its transits to appear and disappear over time. This behavior highlights a key challenge in detecting such planets. Many circumbinary worlds may remain invisible to us simply because their orbits are misaligned. This means our current catalog is incomplete. For every circumbinary planet we have detected, many more likely exist beyond our observational reach. Detection bias hides them from us, not rarity. The galaxy may be filled with worlds circling 2 suns, unseen and uncounted. Beyond Kepler, other missions and techniques have expanded the search. The Transiting Exoplanet Survey Satellite, or TESS, continues the work of Kepler by surveying nearly the entire sky. While TESS focuses on closer and brighter stars, it has already begun identifying candidate planets in binary systems. Ground-based observatories using radial velocity measurements and direct imaging are also contributing, especially for wide binaries where planets orbit only 1 star. Some of the most dramatic circumbinary systems involve extreme stars. There are planets orbiting binary systems that include white dwarfs, remnants of dead stars, or even neutron stars. These environments challenge our assumptions about where planets can survive. In some cases, planets may form after 1 star has already died, assembling from the debris of stellar evolution. These are second-generation planets, born from cosmic destruction rather than creation. Each discovery adds a piece to the puzzle. What emerges is a picture of extraordinary diversity. Circumbinary planets range from hot gas giants skimming the edge of stability to cold worlds drifting far from their suns. Their orbits vary in shape and inclination. Their skies differ wildly, yet they all share a common trait. They exist in defiance of simplicity. These discoveries have forced astronomers to rewrite models of planet formation and orbital dynamics. Binary stars are no longer considered hostile environments for planets. Instead, they're recognized as fertile grounds for complex planetary systems. Perhaps the most profound implication lies ahead. As detection methods improve and next-generation telescopes come online, the search will shift towards smaller, rocky circumbinary planets. Worlds with solid surfaces, worlds with atmospheres, worlds where life could take hold under a double sunrise. As the catalog of planets with 2 suns continues to grow, astronomy stands at the edge of a deeper transformation. The question is no longer whether such worlds exist. It is how common they are, how diverse they can be, and whether any of them can host life that looks back at the sky and sees 2 stars where we see 1. Circumbinary planets have shifted from curiosity to cornerstone, forcing science to broaden its definition of what a planetary system can be. The next generation of telescopes is designed with this complexity in mind. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, has already begun probing the atmospheres of exoplanets. While its primary targets are currently single-star systems, its capabilities extend naturally to binaries. For circumbinary planets, Webb can analyze atmospheric composition, searching for water vapor, carbon dioxide, methane, and other molecules that hint at climate and chemistry. Even subtle variations in temperature caused by two suns could leave detectable fingerprints in a planet's atmospheric spectrum. Future missions will go further. Space telescopes specifically designed to detect Earth-sized planets will not exclude binary systems, as earlier surveys often did. Instead, binary stars will become prime targets. Scientists now understand that ignoring them means ignoring a significant fraction of the galaxy's potential habitats. Improved modeling and longer observation baselines will allow astronomers to detect the irregular transits and gravitational signals that betray the presence of small circumbinary worlds. On the theoretical side, simulations are growing more sophisticated. Supercomputers now model planet formation in binary systems from the earliest stages of disk evolution through billions of years of orbital stability. These models are beginning to show that rocky planets can indeed form in circumbinary habitable zones. They may be less common than gas giants, but they are far from impossible. Some may even enjoy climates more stable than expected, protected by thick atmospheres or global oceans that smooth out stellar variability. The search for life in binary systems also reshapes astrobiology. Life on Earth has proven astonishingly adaptable, thriving in extremes of heat, cold, radiation, and pressure. There is no fundamental reason life could not adapt to the shifting rhythms of a double sun. In fact, variable environments may even accelerate evolution, driving complexity through constant change. On a circumbinary world, evolution would be shaped not just by geology and biology, but by celestial mechanics. Intelligent life, if it emerges, would inherit a worldview defined by motion and duality. Astronomy would be impossible to ignore. The sky itself would demand explanation. Two suns rising and setting, eclipsing one another, drifting across seasons, would imprint a deep awareness of cosmic order and instability. Such civilizations might grasp orbital mechanics earlier than we did, guided by a sky that refuses to be simple. These worlds also challenge our cultural assumptions. For centuries, Earth's single sun shaped mythology, religion, and language. Light versus dark, day versus night. A binary sky would complicate these symbols. Balance might replace opposition. Cycles might replace linear time. Even the concept of a singular center could be replaced by shared gravity, by systems rather than absolutes. From a cosmic perspective, circumbinary planets remind us that our solar system is only one arrangement among countless possibilities. The universe does not favor simplicity or familiarity. It favors what works. And what works, apparently, includes planets that orbit not one star but two. There's a deeper implication as well. If life can arise and persist under two suns, then the conditions required for life may be broader than we ever imagined. The habitable real estate of the galaxy expands dramatically. Binary systems, once dismissed as too chaotic, become promising environments in the search for life beyond Earth. The famous question, "Are we alone?" grows louder and more complex. In the end, planets with two suns are not just astronomical wonders. They are philosophical ones. They force us to confront the limits of our assumptions. They remind us that the universe is under no obligation to resemble our home. And yet, within that strangeness, there may be places that feel familiar in the most profound way. Places with skies, seasons, oceans, and perhaps beings who wonder about the stars just as we do. Under two suns, life would not be lesser or broken. It would simply be different. And somewhere in the vast darkness between stars, there may be a world where dawn comes twice, shadows dance in pairs, and the question of existence is asked beneath a double sky.